All right, so this unit is the vectors unit, and it goes really hand in hand with the projectile unit that we'll be doing next. So it's more of a trigonometry review more than anything, but it also helps to introduce the concept of what a vector is, and also a little bit about force as well, which we haven't really discussed yet. So let's take a look. The definition of a vector has both direction and magnitude. Now that should be very familiar to you, because when we were defining vector quantities versus scalar quantities, one of the things that we said was a scalar only has magnitude, while a vector quantity has direction and magnitude. So this shouldn't be anything new, something you've seen before. Displacement is an example of a vector quantity. Velocity is an example of a vector quantity. Acceleration and force as well. These, of course, aren't the only vector quantities, but these are the ones we tend to come across in physics more than anything. This is the general definition of a force, a push or a pull in a given direction. We'll define it a little differently when we get to actual force unit, but we can stick with this. For this unit, we can stick with this definition. So when you want to represent a vector quantity graphically, you use a vector. Now, a vector really is just an arrow, and that arrow has a certain length, and that arrow points in a certain direction. The length of the arrow would represent its magnitude, so a bigger magnitude, a longer length. And of course the direction is whichever way the arrow is pointing. So this space shuttle, as it's going up into the air, is going up, so that's the vector's pointing up, and a pretty long vector to represent 90 meters per second. So the 90 meters per second would be the length, and then the plus sign would be the arrow pointing up. And then this girl biking, she is going to the right, so we see that's east, and the 20 kilometers per hour would be the length of the arrow. This guy's about to get hit in the face with a certain amount of force, and that force is directed to the right, so we see a plus sign, and we also see our arrow pointing to the right, and he's going to get hit with 100 pounds of force into the face. So we would direct our arrow to the right, and we would give it a certain length to represent magnitude. Of course, pounds is an English unit typically. When we get to the real metric unit of force, we use newtons. Well, here's acceleration as a vector as well. We know that the skydiver is falling down towards the earth, and we know that the acceleration is in a downward direction. Typically that's negative, so we see the arrows pointing down. And the 9.81 meters per second squared would be the magnitude of the skydiver. So of course we have the magnitude, which represents the length, and then we have the arrowhead, which represents the direction of the vector. Now, of course, there are many ways that we can identify direction when we are discussing vectors in physics. And one of the ways that we can describe a direction is cardinal directions. So over here you see a compass. We have north, east, west, and south. And we have a vector that points up and to the right. And we know that this angle, according to our number there, we know that this angle is 40 degrees. And we know that this angle is 50 degrees. Okay? So there are a number of ways that we can identify this vector. We could say that it's 40 degrees north of east. Now again, when you are identifying this part, the north of east part, we say that the north direction is up. So north would be that way, north of east. Okay? Or I could describe it as 50 degrees east of north. So here's north. And east of north would be this direction. Both of those represent the same vector. These values that you see for the sample problem show us that I could say 40 degrees north of east or 50 degrees north of east and still mean the same vector. And we have some other directions here. So let's take a look and see how we would go about identifying where they would be. 10 degrees south of west. Well, here's west, and we're going to go 10 degrees south. So that's going to be approximately right there, 10 degrees, roughly. Now, of course, I don't have my protractor out, so it's not going to be to scale, but it would be just below the west vector there. What else could I call 10 degrees south of west? Well, that would be this angle here. Well, if we know that this is 10 degrees and we know that the entire quadrant has an angle of 90 degrees, then this angle has to be 80. And if it's 80 degrees, we have to give it some context. 80 degrees what? Well, 80 degrees west of south. West of south. Essentially what I do is I just really flip these two words, just like we did up here. It was north of east, then we switched to east of north, so we just flipped those two words. So either one of these would be acceptable, 10 degrees south of west or 80 degrees west of south, though they both represent this vector right here. Well, how about 60 degrees east of south? Let's take a look at where we would try and identify 60 degrees east of south. East of south would be this direction. And 60 degrees would be a little bit more than halfway, more than 45, if 45 is halfway between 0 and 90. So I would say something about right there. So this will be considered 60 degrees east of south, right? Well, could I also write it in a different way? Well, again, what we're saying is, what's this angle here? Well, if you know that this entire quadrant is 90 degrees, then 90 minus 60 is going to give you 30. And that would be 30 degrees south of east. Again, we just switched the number, the words. So 60 degrees east of south and 30 degrees south of east are the same vector. Well, 25 degrees north of west is our next one. 25 degrees north of west, that would be this direction. And 25 degrees, we certainly know that's not halfway, that's less than halfway, so something about right there maybe. And that'd be 25 degrees north of west. Well, what's 90 minus 25? 90 minus 25 is 65, which means this angle here is 65 degrees. And instead of saying north of west, we would say 65 degrees west of north. West of north. Northwest. Well, when you see one that just involves a word without any degrees, that means that it's exactly halfway between north and west. So we're talking about this direction right here. And that would be 45 degrees, of course, if we were going to give it a number. And you could write it either way. You could write 45 degrees west of north. You could write 45 degrees north of west. Or you could just write northwest. That would be acceptable as well. Well, another way that we can describe direction with vectors is what we call angular measurement. And this is a way to take out the use of our cardinal direction words, north, south, east, and west. And we basically look at the X and Y axis as just one big circle. And that one big circle, we have to give it values going around the circle. So this is 0 degrees, this is 90, this is 180, and this is 270. And of course, we also could put 360 instead of 0 degrees. They represent the same thing. That way, any number that you get, there is only one exact vector that could match. You don't have to deal with north of west and south of east and all this other stuff. So if we were going to say, figure out where the 160 degrees is for a angular measurement, the first thing we would have to realize is it's going to be past 90 and before 180. So we know it's going to be in this quadrant here, the 160. And then we have to think about, as far as direction, how far before the 180 is it going to be? Well, what's the difference between 180 and 160? Well, 20 degrees. So that's going to be a little bit above the 180, and that would be represented by this vector here. Okay? 180 degrees, 160 degrees would be this vector here. Now, could you convert this to a cardinal directions? You should be able to. If we were going to use cardinal directions, we would say that this is east, this is north, this is west, this is south, and we would say that this angle, or excuse me, this vector is 20 degrees, and I get that from 180 minus 160, north of west. Or I could do it a third way, and I could identify this angle here. And this angle is, of course, going to be 70 degrees, 90 minus 20. And it's going to be 70 degrees west of north. So you could identify this vector as 160 degrees. You could identify it as 20 degrees north of west, or you could identify it as 70 degrees west of north. Any of those three would be acceptable. Since we're on angular measurement, that 160 is the one we should stick with for this slide. And then we can take a look at these other examples as well. 290 degrees. Well, when we see 290 degrees, we should see that 290 is going to be past 270, so it's going to be well past this one. Well past here. By how much? By about 20 degrees. So that's going to be approximately right there. So that could represent, that vector could represent 290 degrees. Could we write it in cardinal directions? Well, what's the difference between 290 and 270? Well, that's 20 degrees. And 20 degrees what? Well, it's east of south. So east to south, 20 degrees east to south will be the same thing as saying 290. Well, we also could use this angle. Well, what's 20 from 90? That's 70 degrees. And 70 degrees south of east would be another way of saying that. So 70 degrees south of east, 20 degrees east to south, or 290 would all be acceptable. (110 degrees). Well, the 110, we know it's going to be past the 90. How far past the 90? Well, what's the difference between 110 and 90? Well, 110 and 90 is 20 degrees difference. So 110 would be about right here. So we could say 110 degrees, or we could say this angle here, which is what? Well, what's 110 minus 90? That's 20 degrees. And that's west of north. Or we could use this angle here. What's 90 minus 20? 70 degrees. North of west. So 70 degrees north of west, 20 degrees west of north, or 110 degrees. Either way is acceptable. How about 135? Well, 135 we know is going to fall right in the middle of 90 and 180. So if we were going to try and figure out how far past 90 degrees is 135, we would just say 135 minus 90. And 135 minus 90 is 45 degrees. So we know that's halfway in between. So about right there. So that could be 135, or it could be 45 degrees. And again, that's 135 minus 90, west of north, or 45 degrees north of west. Or you could just say, since it's halfway between, you could just say northwest, and that would be acceptable as well. And 350 degrees, well, that's practically all the way around. It's just short of 360. Remember, we said this could be 360 as well, not just 0. So how short of 350 is 360 is 350? Well, it looks to me like it's 10 degrees. So 10 degrees below the 360 line would be about right there. So that could be 350 degrees, or you could say, well, what's this angle? It'd be 360 minus 350, so 10 degrees south of east. Or we could say, well, what's this angle here? Well, what's 90 minus 10? 90 minus 10 is 80 degrees, and that would be east of south. So 350 degrees, or 80 degrees east of south, or 10 degrees south of east. All right, so how do we handle multiple vectors? Well, there's two ways to do it. One way is called the head-to-tail method, and the other way is the parallelogram method. Let's talk about head-to-tail method first. It's basically when you have vectors that are connected one after the other. So we have a vector we can see is this way, and then from that vector we have another pointing this way, and then from the vector we have another pointing this way. Each one adds to the other. So you see the tail and the head meet, and that's why it's called head-to-tail method. Okay? Parallelogram method is when you have two vectors that have the same starting point. So let's say I was pulling one direction on a big boulder or rock or something we're trying to move, and you're pulling in another direction. We would be applying a force to this, whatever this object is, a boulder. So our two forces would have the same origin. We're both starting or pulling from the same, the boulder. And that means that the way that we would identify the method would be the parallelogram method. Well, from this combining of vectors, we can get what's called the resultant. And the resultant is the combined vector of multiple vectors. So if we were going to do this one down here, and I had a vector here, and I had a vector here, and I had a vector here, and I wanted to find the resultant of those vectors. Well, what I would say to myself is I would draw a line directly from the beginning of the first vector, so right here, and the end of this last vector, right here. So the combined resultant, the combined vector for all three of these vectors would be this red line. And it's drawn from the tail of the first to the head of the last. That is the rule. So if I had, say, an arrow here, an arrow here, and an arrow here, and I said draw the resultant, well, this is the tail of the first, and this is the head of the last. So I would draw from the tail of the first to the head of the last, and that would be my resultant for those combination of vectors. Well, what if I had, say, a vector there, a vector there, and a vector there? Well, now, where I started and where I finished are the same position. So there is no resultant. It's zero. Because the tail of the first vector and the head of the last vector are all in the same place. No resultant. The parallelogram method for drawing the resultant is a little bit more complicated. This idea of drawing an overall resultant is the same idea as the resultant in the head-to-tail method, but getting it is a little harder. So let's say that you had a vector pulling from a source of that direction, and you had another vector pulling this way. And we were going to figure out what the resultant would be. Well, what you have to do is you have to think of it like a copy and paste sort of method. If I take this vector here and I add it to the end of this vector, so I'm just trying to get a mirror image from here to here. And then I take the vector here, this one, and I place it here to here. So again, I've taken this vector and I've placed it there, kind of a mirror image of the vector that we have right here. The combination of these two vectors will be drawn from the origin to where those two meet. So this red line would be my resultant. And you can kind of see it better here. This vector I transitioned over to this side. And this vector here, the one in red, I transposed it over to here. And from that, we get the purple resultant. That's what this purple line would be. Drawn from the origin to where they meet, where the two dotted lines meet. Let's say we had a vector there, and we had another vector, say, here. Well, I would take this vector, and I would draw a carbon copy of it from the end of the first vector, the longer vector. And then I would take this vector here, and I would draw a carbon copy of it right there. And then I would draw from the origin to where those two vectors met. And that would be my resultant in blue. So the parallelogram method, we'll practice some more in class. It's a little more complicated and much harder to explain in this type of format than it would be if we were working problems out together. But we will definitely practice that in class. Mathematically combining vectors, we do this quite a bit in physics. And we start off with a couple of basic ones here. And what we're doing is we're trying to get the resultant of two vectors that just happen to be pointing the same way. We have a vector that points 20 miles to the east, and we have a second vector that points 35 miles to the east. So these are in the head-to-tail method. And what we want to do is we want to figure out what the resultant would be for this combined, for the blue and the yellow vector. Well, if you think about it, if we did the head-to-tail method and we drew the resultant, it would be from the tail of the first vector to the head of the second one. And we'd end up with a line that looks like this green line down here. It's just a combination of the blue and the yellow turning into the green longer vector. But we would have to actually take the values, in this case 20 miles and 35 miles, and we would add them together. Why would we add them together? Well, because they're both pointing the same way. So 20 plus 35 gives me 55 miles. And then, of course, I would continue with the direction east as my answer for the resultant, 55 miles east. This could be like if a plane was flying in a certain direction and the wind was going in that same direction. Well, you would combine the wind speed with the plane's speed to get the total resultant speed. Well, now we have a situation where our vectors are pointing opposite of each other. So we have 20 miles east and 35 miles west, but the difference is the arrows are pointing opposite ways. Well, if that's the case, then instead of summing the vectors to get the resultant like we did on the previous slide, for this problem we would have to subtract them. And it would be 20 from 35. The difference between 35 and 20 is 15. 15 miles west. Why west? Well, the 35 miles west is greater than the 20 miles east. So I know the difference in the two values as far as magnitude goes is 15, 35 minus 20. But the overall direction is going to be whichever one of these vectors had the greater magnitude. And the greater magnitude is definitely the 35 over the 20. This, again, could be a plane flying into the wind. The plane has a certain velocity without the wind. The wind is pointing against the plane. So if you wanted to find the overall velocity, you would have to subtract the wind's velocity from the plane's velocity. Or you could think of a boat going upstream. The stream is pulling down the river. The boat's going up the river. So the difference in the two values would give the overall velocity of the boat. You could think about it if you've ever been to the airport, the moving sidewalks. If you are on the moving sidewalk and you're walking with the moving sidewalk has a certain velocity, and you're walking with a certain velocity, so you would combine those to get your overall velocity. But if you are doing what, of course, they don't want you to do, and you're walking in the opposite direction of the moving sidewalk, you would have to subtract your velocity from the velocity of the moving sidewalk to get the overall velocity of you. So this would be the resultant vector between the blue and the green vectors. Okay, so how do we handle resultants if the vectors we're trying to add or subtract are not along the same plane? For example, if I have a vector pointing up and a second vector pointing up, and I wanted to combine these two vectors, I would just add them together because they're along the same plane. Or if I had a vector pointing to the right and one pointing to the left, again, these are along the same plane, so I would just subtract them to get the overall resultant. But in this case, we have a couple of vectors that are not along the same plane. We have one that's in blue that's pointing to the right, and we have one that's in yellow that's pointing up. So how do we handle situations like that? Well, what you're going to have to do is you're going to have to go to some trigonometry. And there are two main things with trig that we tend to use a lot of in physics, and that is the Pythagorean theorem, a squared plus b squared equals c squared, and SOHCAHTOA. Now, if you don't know what SOHCAHTOA means, so is the sine is opposite over the hypotenuse. Ka is cosine is and then of course it's the sine of the angle. Usually our unknown for an angle is theta, and theta has this little circle with the line going through it. Cosine is adjacent over hypotenuse, and TOA is tangent, and that's opposite over adjacent. And this is just a mnemonic device that you've probably heard before about how to keep track of the order in which you solve for any of the trig functions. And of course, the Pythagorean theorem, the A and the B, those are the legs of the right triangle. So it doesn't matter whether you label this one A or B, whatever you label it, the other one's got to be the opposite. And of course, C is the green. C is the hypotenuse. So if we were to go through and solve for this green line, now again, let's imagine that this number is not here. This value isn't here. This is unknown. 25 miles is the unknown. And you were asked to find the value of the resultant. Well, how would it look just on paper before you drew it out? Well, we'd have one vector pointing this way. We'd have another vector pointing up. Now, of course, they are together in the head-to-tail method. And so what do we do in the head-to-tail method? We draw from the tail of the first vector to the head of the last vector. So this value here is the hypotenuse. And we'll just label this A and this B. And we'll solve for the hypotenuse. A squared plus B squared equals C squared. We're solving for C. So C would be the square root of A squared plus B squared. And then we start plugging in our numbers. The square root of 20 squared plus 15 squared. And that gives us the square root of 400 plus 225. And the square root of 400 plus 225 gives you the square root of 625. And that would give us 25 miles for our resultant value. Now, of course, that does not include the angle. On this one, we're just sticking with solving for the resultant magnitude without the direction. Now, we could find the angle, and I'll take you through that right now. The angle is going to be found using an inverse trigonometry trig function, sine, cosine, or tangent. We just got to figure out which one to use. And they were giving us 15, they were giving us 20. So they were giving us the opposite side, and they were giving us the adjacent side. The 25 we had to solve for. So opposite over adjacent, which function shall I use? Well, it's going to be the tangent. And since we're finding the angle, it's going to be tangent theta, and theta is our unknown, equals the opposite side over the adjacent side. And that means we're going to have tangent theta equals opposite side. What's the opposite side? It would be the 15 over 20, the adjacent side. And now we got to think of how do we, when we're in algebra, and we have to do the opposite of the function. So what's the opposite of tangent? Well, the opposite of tangent is what we call the inverse of that function. So in this case, it'd be the inverse tan, sometimes called the arctangent. There's lots of different names for it, but it would look something like this. If we take the inverse tangent of tangent, it becomes theta. So we get rid of the tan. And then on the other side, it would look like this, tangent -1. That -1 just stands for the inverse tangent of 15 over 20. And you could type that directly into your calculator, and you got to make sure that when you do it, you do use the inverse function of the tangent, not just tangent. And we end up with 36.86. I usually do my degrees to the tenths, so 36.9 degrees. And then we know that this is east and that's north, so this angle is 36.9 degrees north of east. Now we could also have used, if you remember earlier we did cardinal directions, you could address it from the other axis, from the north axis. So we'd have to subtract 90 or 36.9 from 90, and that would be 53.1 degrees. And then remember how we switched the lettering? It would be east of north. So if you're looking at a compass, this angle would be the 36.9 degrees, and this angle here would be the 53.1 degrees east of north. Either one would be acceptable. So you would write, if you remember our answer was 25 miles. 25 miles, 36.9 degrees north of east would be the overall vector for the resultant, the green vector here. Now in physics, we have specific names for the legs of the right triangle, and we call them components. And the components are labeled by the axis that they fall on. So if a component falls on the x-axis, we label it the x component. If the component falls on the y-axis, we call it the y component. And every resultant, the resultant being this green vector here, is going to have connected to it an x component and a y component. And I have a lot of students that they'll get confused and they'll say, well, the x component and the y component, couldn't you draw it like this and say that this is the y component and this is the x component? Yeah, you can do it that way. It's perfectly acceptable to draw it that way. You just have a big rectangle, a big rectangle when you're drawing it out. And you know if this value is a certain number, then this value has to be the same number. And if this value is a certain number, then this value has to be the same value, opposite sides of a rectangle. So it doesn't matter which one you choose. Typically, I guess it really depends on how you draw it out, but usually we draw the x component first and then the y component. And when you do that, you just end up with this shape down here. There's always going to be a right angle for any intersection between two components. So we have the x and the y component intersecting here, so we see there's a right angle. So if I have a resultant pointing like that, and I wanted to draw the components, I could draw an arrow this way and an arrow up, and we see that there's a right angle right there. I could also draw on the y-axis first, the y component first, and the x second, and there's another right angle. So either one of these would be fine, the way it's drawn up there. All right, so we're looking at a resultant in green. We wanted to draw the x and the y component. We would simply decide to draw either the y component or the x component first. So I could draw this one here. And remember, when you're drawing components, you're always making them at a right angle. So I would draw the x component to the left. Remember, we're trying to connect with the end of the head of the resultant vector. So there's a nice right angle right there. But if I could also do it this way. There's my coordinate plane. Here's my vector. You could also draw the x first and then the y component, like so. And you end up with a right angle here. So either one of these would be acceptable for drawing the x and the y component. It really doesn't matter which one you choose to do, just as long as the connection between the x and the y always make a right angle, you should be good. And remember, you always draw from the origin towards the head of the resultant vector. Never draw from the resultant head back to the origin. Always draw away from the origin. All right, so this problem, we are given a hypotenuse of 50 miles, and we're given an angle of 20 degrees. So this angle here is 20. And we have to solve for the components of the right triangle. Of course, there's our angle, right triangle right there. So there's a couple ways to approach this. Doesn't matter which one we start with, adjacent or opposite. I'm just going to start with the opposite first. And when we do that, we decide which one of these trig functions is going to work for us. Are we going to use sine, cosine, or tangent? Well, I'm trying to find the opposite, and I know the hypotenuse, and I know an angle. So this opposite side and this hypotenuse is what I want to go after. So I'm going to be doing sine. So I'm going to say the sine of the angle is equal to the opposite side over the hypotenuse. And I know that if I rearrange this, that the opposite side, which we could also call the y component, that's y component, is equal to the hypotenuse times the sine of the angle. So our y component would equal the hypotenuse, which is 50, times the sine of theta, and theta is 20 degrees. And I probably should have mentioned this before, but when you are dealing with a scientific or graphing calculator and you are working with trig functions, it needs to be in degree mode. If you are in radians, you will end up with some wrong answers. The calculator has to be told if you're dealing with circles or triangles. So we are dealing with triangles in this unit. So we want to make sure it's in degree mode when we're working these out. And when you do 50 sine of 20, you get 17. And what unit would that be? Well, that would be miles. And that's going to be north. 17 miles north. And then to find the adjacent side, we have a couple of options. We could use the Pythagorean theorem and use our 50 and then also our answer from the first problem. But then we're depending on that first answer, the 17. So is there a way we could find the adjacent without using our answer from the first part? Yeah, we could use the cosine function. We could use the cosine function, which says that the cosine of the angle is equal to the adjacent side divided by the hypotenuse. And of course our cosine theta times our hypotenuse is going to give us our adjacent side. And our adjacent side could be written as the x component instead of the adjacent side. And our hypotenuse is 50. And our cosine of the angle is 20 degrees. So when we plug in our values, 50 cosine of 20, we end up with 46.98. We end up with 47 miles, and that would be east. So our x component is 47 miles east, and our y component is 17 miles north. So we're saying that this object moved 47 miles east and 17 miles north over a span of 50 miles.